All right. In our last installment, what we talked about was our modern understanding of the atom and how we have come to understand the atom as it is today. So we talked about the fact that the nucleus is a dense center of the atom that contains both protons and neutrons, positively charged protons and neutral neutrons. And the electron is negatively charged, and the electrons are embedded throughout the atom like plums in a plum pudding. So that, up to this point, is our understanding of the atom. So what we want to do now is take a look at the work of an individual in 1942 whose name was Niels Bohr. Now, Bohr was a very important part of the development of the atom because he looked at the atom from a mathematical point of view. And through a series of complex mathematical equations, he comes up with a new model. According to Bohr, the electrons around the nucleus are not stationary, like plums around a plum in a plum pudding. These tiny negatively charged particles, Bohr believed, moved around the nucleus in specific orbitals like planets around the sun. Okay, so if you think of the planets moving around the sun in our own solar system, that's how Niels Bohr thought of the electrons. The electrons moved around the nucleus like planets around the sun. So this is what the model might look like, right? So in the center of the atom, we had these positively charged protons and these neutral neutrons. And then in the periphery, we had these electrons, which according to Bohr, moved in these specific orbitals around the nucleus. Although the Bohr model of the atom is not thought to be entirely correct, it is very useful in explaining many of the attributes of the atom. And Bohr's model of the atom is the one which we most easily recognize, but even then, it's not exactly correct. In 1956, Austrian physicist Erwin Schrödinger came along with a model of the atom based on probability. This is known as the cloud model of the atom, which we believe to this day is the true nature of atoms. Electrons do not orbit, according to Schrödinger, but rather they are assigned a probability of existing in a certain specific energy level. So in the same way that, for example, if I were to call your parents on the phone and say, "Where is your child?" they would have a high probability of knowing. There would be a high probability that you would be in a specific room. If, for example, you were in another class at that time, in math class, you would have a high probability of being in that class. There's not an absolute certainty that you're in that classroom. You may have gone to the bathroom, or you may have gone to receive an award at the dean's office. Whatever the case may be, there is some probability that you're in a specific location. And so Schrödinger assigned probabilities to electrons and created these clouds of electrons. So in the center, for example, he said there was a very high probability of a cloud existing or electrons existing next to the nucleus. And then there was a low probability area. And then there was a high probability area again, and so forth. And so that's the way it worked, according to Schrödinger, that you couldn't tell where the electron was. You could only tell where the electron had a high probability of being. So now the picture is complete. The atom is the building block of nature, and an atom is composed of positively charged protons and neutral atoms or neutrons in the nucleus with negatively charged electrons in the periphery. So now let's move on to an important question. Here it is. What defines an atom? What is an atom? What's the difference between a carbon atom, say, an oxygen atom, or an atom of iron? The answer is the number of protons. So the number of protons defines the atom. All carbon atoms have 6 protons in the nucleus. However, some carbon atoms have 6 neutrons, while others have 8. These are known as isotopes. Okay, so for example, once again, let's take, for example, carbon. All carbon atoms have the same number of protons, right? But some carbon atoms have 6 neutrons and others have 8. So these are called isotopes. The number of protons in the nucleus is known as the atomic number. So the atomic number is the number of protons in the nucleus. The atomic number for carbon is 6, since there are 6 protons in all carbon atoms. So all carbon atoms have 6 protons. Again, though, not all carbon atoms have 6 Neutrons, some have 6, some have 7, some have 8. These are called isotopes. Now, the mass number is the number of protons plus the number of neutrons. The mass number is protons plus neutrons. Protons and neutrons are about the same mass, which is a 1 atomic mass unit, or AMU. So while electrons are much, much smaller and exist outside the nucleus. So if you can imagine having one proton or having one neutron sitting on the palm of your hand, it would weigh about 1 atomic mass unit, or 1 AMU. Now, protons have a charge of +1, and neutrons have a charge of 0, and electrons have a charge of -1, right? So once again, protons +1, neutrons 0, and electrons have a charge of -1. Atoms are neutral and have the same number of protons as electrons. Ions, on the other hand, have different numbers of protons and neutrons. For example, an oxygen atom has 8 protons in the nucleus. If there are 10 electrons present, the atom has a charge, it's an ion, first of all, and it has a charge of -2, since there are 2 more negatively charged electrons than protons. So remember, atoms are neutral, but ions are charged. Elements on the left side of the periodic table gain electrons to become positively charged. Elements on the right side Elements on the left side of the periodic table become positively charged by losing electrons. Elements on the right side gain electrons to become negatively charged. Okay? Positively charged ions are called cations. Negatively charged ions are called anions. So cations are positively charged, anions are negatively charged. Folks, just a quick correction to make on your notes. Here it says on this line, it says elements on the left side of the periodic table gain electrons to become positively charged. They don't gain electrons, they lose electrons. Okay, so change that on your notes. They lose electrons to become positively charged. And then this is correct. Elements on the right side of the periodic table will gain electrons to become negatively charged. Okay, so we've talked about ions that have different numbers of protons and electrons. So now let's talk about isotopes. Isotopes are atoms which have the same number of protons but different numbers of neutrons. For example, let's take carbon atoms. All carbon atoms have 6 protons in the nucleus, but not all carbon atoms have 6 neutrons as well. Some atoms of carbon have 8. We'll call the various versions of carbon with the same number of protons but different numbers of neutrons isotopes of carbon, right? We can denote these 2 different isotopes of carbon as shown below. The C, of course, is the symbol for carbon. The subscript 6 denotes the number of protons. It's always 6 for carbon. And the superscript denotes the mass number, which is the number of protons plus neutrons. So if I look at the carbon box on the periodic table, right, I notice that it's just a carbon. It's just a C. That C stands for carbon. But there are multiple isotopes within that box. So if I see a 6 on the bottom, for example, I'm going to have 6 protons in that carbon atom. In fact, there have to be 6 protons in that carbon atom, because if it didn't have 6 protons, it wouldn't be carbon. But notice the difference in these 2 isotopes. This is carbon 12. This is carbon 14. Carbon 12 has a total of 6 protons plus 6 neutrons. Carbon 14 has 6 protons plus 8 neutrons for a total of 14 protons and neutrons. Carbon 12 on the left, carbon 14 on the right then. Let's denote that again. So on this left side, this is carbon 12. On the right-hand side, carbon 14, just like that. All right? Now, we can also simply write the mass number after the name of the element. For example, we can write carbon-12 or carbon-14, just like that. Now, if we know the relative abundances of each of the isotopes for a given element, we can calculate the average atomic mass for that element. So you're certainly going to need to be able to calculate the average atomic mass. You can calculate an average atomic mass in exactly the same way you calculate your chemistry grade. It's a weighted average. The average atomic mass is the weighted average of the masses of the various isotopes for an element. So let's take a look at an example. Here's the problem. It says calculate the average atomic mass of potassium. Now, potassium has 3 isotopes with the following atomic masses: potassium 39, potassium 41, and potassium 40. Notice all of them have the same number of protons, 19, 19, and 19. If they didn't have 19 protons, they wouldn't be potassium. But this isotope, isotope 39, has 20 neutrons, 22 neutrons for the second type, and 21 neutrons for this, right? So 19 plus 20 again is 39, 19 plus 22 is 41, 19 plus 21 is 40. But they're not present in the same abundances. Potassium 39 is present in the universe in this percentage, 93.9%. Potassium 41, 5.81%. And potassium 40, only 0.02. So we're going to use these weighted averages to help us to calculate the average atomic mass. So here we go. First, change the percentages to decimal places, and then multiply those by the mass number. So, for example, 93.90 becomes 0.9390. 5.81 becomes 0.0581, and 0.02% becomes 0.0002 times, again, multiplied by the mass numbers. When I do, these are the values that I get, 36.621. I'll round that to 36.62. That has 4 significant digits. The 2.381, 2.38, 3 significant digits, and the 0.008 remains 0.008 with 1 significant digit. When I add those up, I get this number, 39.01. 39.01 AMU. So that's the average atomic mass then for potassium. Okay, now that we've had the opportunity to look at how to calculate average atomic mass, I want you to try this one. Element X has 2 known naturally occurring isotopes. The mass and relative abundance of each isotope are shown below. Relative abundance of the first one is 50.57. Has a mass of 78.92. The relative abundance of the second one is 49.43. It has a mass of 80.92. So what is the average atomic mass of element X to the nearest hundredth of a mass unit? Okay? All right. So let's take a look at this one. So the relative abundances need to be converted into decimals. I'll do that by moving the decimal place over 2 times, 1, 2 to the left-hand side. So 50.57 becomes 0.5057. 49.43 becomes 0.4943. I'm going to multiply those by the masses in AMU, 78.92 for the first one, 80.92 for the second one. And so now what I've got is I've got these 2 numbers right here to the nearest hundredth. I'm going to add those together. 39.91 plus 40.00 gives me 40.91 AMU. That is the average atomic mass, and that'll do it for this installment. I'll see you in the next one. Thanks. Bye-bye.